All right, hello everyone, and welcome to our 8th lesson in Unit 4, which is on Introduction to Acid-Base Reactions. So today's objective is to identify species as Bronsted-Lowry acids, bases, and/or conjugate acid-base pairs based on proton transfer involving those species. Today you should know that by definition, a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. In aqueous solutions, water plays a very important role in many acid-base reactions as its molecular structure allows it to accept protons and donate protons to dissolved species. When an acid or base ionizes in water, the conjugate acid-base pairs can be identified and their relative strengths can be compared. Before we look at acid-base reactions, let's review how we name binary acids. So a binary acid is made up of hydrogen plus one other element. When we name these, we use the pattern hydro plus the root of the element plus ic, and then we add on the word acid. So for example, if we're looking at HCl, we have hydro and then chlor is the root word, so it'd be hydrochloric acid. If we had HF, that would be hydrofluoric acid. HBr would be hydrobromic acid, and so on and so forth. All right, and then when we are working with acids that contain hydrogen in a polyatomic ion, they have a different set of naming rules. So first you're going to identify the polyatomic ion within that acid. Then you're going to change the ending. So ate gets changed to ic and ite gets changed to us. I always tell my students to remember the words mathematic and tendinitis. If you want to remember that way, that would be great. If not, you can find another way or just memorize it. I've also had a student tell me that she ate so much that it gave her the ick, if that helps you, but she didn't have a good one for ite to us. So, and then after you change the ending, you're going to add the word acid to the end. So let's do some examples. First one, H2SO4. Our polyatomic ion present is SO42 minus, which is sulfate. So we're going to change the ending ate to ic. Now sulfur is one of those weird elements where we don't just use the root of the word, we use the entire word. So just keep that in mind. So this would be changed to sulfuric acid. Then we have H2CO3, which has CO32 minus or carbonate. Carbonate gets changed to carbonic acid, and that would be our name. HNO2 has NO2 minus, which is nitrite. So nitrite changed to nitrous acid. And then finally, we have PO43 minus in this acid, which is phosphate. So that's going to change to phosphoric acid. Same as sulfur, this one uses more than just the root of the word. All right, so I just wanted to review our strong acids and our strong bases because they are very important to have memorized. Remember, our three from the periodic table are chlorine, iodine, and bromine. They are right here in a row on the periodic table. I have had a few students say Clobri to help them remember, but if you just want to remember them, that would be great. And all of those assume -1, so we only need one hydrogen for those. So that would be HCl, HBr, and HI. And then for our polyatomic ion acids, we can use that little jingle that we went over in class, which is clo, clo, no, so, 3, 4, 3, 4, and then just add your hydrogens. So one more time, clo, clo, no, so, 3, 4, 3, 4, and then you add your hydrogens based on the charge of that polyatomic ion. So for ClO3, that's only a -1 charge, so you only need one hydrogen. ClO4 is also only a -1 charge, so you only need one hydrogen. NO3 is only a 1 charge, so you only need one hydrogen. But SO4 2 minus, so you need 2 hydrogens. And then for our strong bases, it's kind of nice because they make a B for base on the periodic table. So if you look at group 1, you go from lithium all the way down to cesium, go to barium, and up to calcium. So it makes a lowercase b on the periodic table, and then you just add your hydroxides. Obviously, for our group 1 metals, they only form a +1 charge, so we only need 1 hydroxide. But for our group 2 metals, they form a +2 charge, so we need 2 hydroxides. So in AP Chemistry, we use the Bronsted-Lowry definition to describe acids and bases. We know by now that a Bronsted-Lowry acid is a proton donor and a Bronsted-Lowry base is a proton acceptor. So whenever you see that term Bronsted-Lowry, you should immediately think about the transfer of a proton, which is the H+ ion. So we represent an H+ ion as a proton because a neutral hydrogen atom has 1 proton and 1 electron. And when hydrogen loses its electron to become H+, all that remains is that proton. So in acid-base reactions, the particle that moves between species is literally just the proton, but we write that down as H+. All right, we can see in this reaction on the right here, HCl donates an H+ ion to NH3. So HCl is acting as the acid and NH3 is acting as the base. Once HCl loses its proton, it becomes Cl-, which is the conjugate base. And once NH3 gains a proton, it becomes NH4+, which is the conjugate acid. So conjugate acid-base pairs differ by just 1 proton. And we can use this idea to talk about strength. So if an acid donates H+ easily, then its conjugate base is going to be weak because it has very little tendency to take that proton back. Likewise, if a base accepts H+ easily, its conjugate acid is going to be weak. So strong acids form weak conjugate bases and strong bases form weak conjugate acids. So let's do a little example with identifying our acid, our base, our conjugate base, and our conjugate acid. So remember, I like to do this finding my conjugate acid-base pairs, and those only differ by 1 proton. So if I'm looking here, I have water, it turns into hydronium. I know it went from 2 hydrogens to 3 hydrogens. So since it accepted a proton, water here would be my base. And that turns into my conjugate acid. And then for our other conjugate acid-base pair, we have H2S forming HS-, which means this was an acid because it donated a H+ ion and became a conjugate base. All right, so this is the very first part of an FRQ. It says the reaction between hypochlorous acid and water is represented above. Identify one of the conjugate acid-base pairs in the reaction. So we talked about this a few times already, but I want to reiterate that when it says to identify a conjugate acid-base pair in an acid-base reaction, there are 2 potential answers, and you can only do one or the other, and they have to be specifically those pairs. And remember, the definition of a conjugate acid-base pair is differing by 1 proton. So if we're starting with HClO, the pair to that is going to be the one that is only differing by 1 proton. So our first conjugate acid-base pair potential answer would be HClO aqueous and ClO- aqueous. Now you could also write your answer as our other conjugate acid-base pair, which is H2O liquid and H3O+ aqueous. Now, again, you can either write the blue as your answer or the yellow as your answer. You cannot have both, and you cannot have a mix of the 2. This next question from a past AP exam says the Bronsted-Lowry bases in the reaction represented above are, and then you have to identify them. One thing we have not gone over yet, which we will definitely go over in Unit 7, is these double arrows here. This means that we have an equilibrium, which means we can go both directions in the chemical equation. So we can go towards the products or we can go towards the reactants. So essentially what this is saying is what is acting as the base if we are moving to the right towards the product side, and what is acting as a base if you're moving to the left or to the reactant side. So you can just kind of imagine it as flipped. So we're used to seeing it like this, but with this double-headed arrow, you can also kind of imagine it going the other way, which is the products as the reactants. So now let's identify our base in both of these equations. So remember, the base is the one accepting a proton, and we can see that NH3 goes from NH3 to NH4+. So that is the one accepting the hydrogen. So NH3 is the base in this reaction. And then in the alternate one, or the one going backwards, you can see that our Cl- is going to be the one that accepts the hydrogen. So this will be our base going the opposite direction. So the answer for this one would be B, NH3 and Cl-. And then we have another multiple choice question. It says a 10 milliliter solution of an unknown acid HA is titrated with 0.2 molar NaOH. The reaction occurs during the titration is represented by the following equation. Which of the following is a conjugate acid-base pair for the reaction that occurs during the titration? So again, conjugate acid-base pair, differing by one proton. So we have HA and A+, or our other option is going to be OH- and H2O. So that specific one is going to be our answer, which is D. So some substances can act as an acid or a base depending on what they're reacting with, and we call these substances amphoteric or amphiprotic. Two important examples you should know for the AP exam are water, which is H2O, and ammonia, which is NH3. They are amphiprotic or amphoteric because they have both a lone pair that can accept a proton and a hydrogen that can be donated as a proton, so they can do both. So water can donate a proton and act as an acid, forming OH-, or it can accept a proton to act as a base, forming H3O+. So how can I tell if something can donate or accept a proton? To decide whether something can donate a proton, what we're doing is looking for an acidic hydrogen. An acidic hydrogen is one that is attached to a highly electronegative atom like oxygen or nitrogen. So if we see an OH bond or an NH bond, that hydrogen can be donated as a proton. In the structure on the bottom here, we see that hydrogen that's attached to the oxygen. That is the most acidic hydrogen in this molecule. So if it were to donate a proton, that is where it would be coming from. And then to decide whether a substance can accept a proton, we need to look for a lone pair of electrons. So a molecule or ion can only be protonated if it has a lone pair available to form a bond with the incoming proton. And just a side note here, even though having a lone pair is required to accept a proton, not every molecule with a lone pair can actually accept one. So the central atom has to be able to form another bond without exceeding its stable bonding capacity. All right, so let's put that into action. This one says, based on the Bronsted-Lowry theory of acids and bases, which of the following species can act as both a conjugate acid and a conjugate base? So we want to know which one of these are amphiprotic, meaning they can form a conjugate acid and they can form a conjugate base, which means they can donate and accept a proton. So looking at HS minus, my structure looks like this, which means technically I could lose that hydrogen because sulfur is pretty electronegative and form S with a full octet and a 2- charge. Or I could take that HS minus and I could donate one of those lone pairs as a bond between an incoming proton. So that would form H 2s. So A is actually our answer because it can do both. But let's talk about why B, C, and D are wrong. So looking at CH3COO minus, I can already tell that I do not have an acidic hydrogen because my only hydrogens are attached to a carbon, which means I do not have any hydrogens to donate. So B would not be the correct answer. Now I can very easily accept an H plus ion on that oxygen on the end there, but I cannot donate it. So that's not the answer. Then with C, C right now is H3O plus. Now we are very well aware at this point that hydronium can lose a proton and become H2O, which is pretty stable and a nice little reaction. However, can it add on a proton? And the short answer is no, but the reasoning, there are a few, is one, it's completely unstable if it were to happen, which technically it could happen, but it's very unstable because it forms an oxygen with 4 single bonded hydrogens and a +2 formal charge on the central atom, which is highly unstable. Also, hydronium is a positive ion, so the fact that a H plus ion is going to be attracted to it and want to come and bond with it is highly unlikely because those are 2 positive charges. So for C, it's going to easily be able to donate a hydrogen, but it's not going to be able to accept a hydrogen very easily. So that is not the answer. And the same goes for NH4. We can definitely donate an H plus off of NH4 and that would become NH3. However, if we look at NH4, we already have nitrogen with 4 bonds and there is no lone pair on the nitrogen. So there's nowhere for that hydrogen to come in and bond to. And also nitrogen is in period 2, which means it can only have an octet, cannot have an expanded octet. So that is why A is the correct answer. I hope this video helped you. If you need any help or want to have any questions answered, please let me know or leave a comment in the video. Have a great day. Bye.